Well, this is John Buck, Super Chemist, here to go over what valence electrons are. And this is, the last couple of videos I was like, you should know this, or at least know the gist of it. This here, you need to know. This is a very, you can't learn anything else until you learn this. But it's a simple concept. Valence electrons are just the electrons in the most outer shell. Okay? Remember I said a shell, you can think of it as a floor. Shell 1 would be floor 1, shell 2 would be floor 2, and so on. Okay? And if you think about it, those electrons, they're the ones that are involved in chemical reactions. Okay? And the reason why, because the further away an electron is from the nucleus, the less influence the nucleus has on that electron. It'd be like if you were, it's not gravity, I think it's called Coulomb force, but it's the same type of concept. Think about a person on planet Earth and someone orbiting over, in orbit. Who's easier to pluck off? You know what I mean? Pluck off the planet. The guy in outer space is, you know what I mean? He's further away. The planet has less, influence on that person than it would a person that's on Earth or, floor up above Earth. All right, and how do you find your valence electrons? Well, remember last time we did electron configuration, and that gave all the electrons on the atom. Now let's look at this periodical chart. Remember that the rows going left to right, those are called periods, and they sync up with your shell or your floor number, okay, until you get down to the d orbitals. Then it gets kind of weird, remember? But the columns going up and down, those correspond to something else. Those correspond to your valence electrons, okay? And if you think about it, let's take lithium for an example, okay? This first shell we don't care about because they're not, the valence electrons are in the most outer shell, right? And lithium has an electron right here in this shell 2 or period 2, right? So that's the only electron we care about, and it only has one in that second shell. And you notice that all of these in this first row, they all, they fill out their row, and then you come down to where they're at, and they only get one electron. Same with potassium. You'd fill out this whole row, and then you would give one to potassium. That would be the only valence electron that potassium has, okay? So if you want to know how many valence electrons something has, everyone in the first row has one, everyone in the second row has two, and if you go over here, these is where it'd be 3, 4, 5, 6, 7, and 8, all right? And then you filled up your row. Now, or your shell, you filled up your shell. But you see hydrogen, remember it only has an S, it has no p orbitals. So it fills out its shell by only putting in 2 electrons. Helium has 2 protons and therefore 2 electrons, and it has filled up its shell. So hydrogen would have 1 valence electron, all right? Boron, see how it's in the third row, 1, 2, 3. So it would have 3 electrons. Okay. If you go down to here where there's, say, let's do the first d orbital one. This is the 4th shell. Okay. But for the d orbitals, that's the 3d. Okay. So these 3ds, they're in a shell or a floor below these 4s, right? They're on floor 3 and they're on floor 4. So the valence electrons are only on the top floor. You know what I'm saying? So there'd be 1 for potassium, 2 for calcium, and you would come over here. There'd be 3 for this, blah, 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 because these are in a lower orbital. I mean, a lower shell, a lower floor. Okay, so they're not valence. All right, so if you get up to here, we have bromide, right? You'd have your 2 s electrons, and you'd have 5 p electrons in this outer shell. You only care about the last shell, right? So that's 7 electrons. And if you notice, they're numbered 1, 2, and I skip over the d's. 3, 4, 5, 6, 7, 8. All of these in this row have 8. All these have 7 and 6. You know what I'm saying? It counts down all the way down to 1. So your periodical chart just tells you, you can just look on it and know. You know what I mean? Carbon. What does it have? Well, you come over to the same shell. You can see it has 1, 2, 3, 4. It has 4 valence electrons. It's basically that simple. Like I said, they're the reasons for the chemical reactions. You know what I mean? The other electrons are so tightly in there, they're too close to the nucleus to be plucking them off and doing stuff with them. So let's take chromium for an example, okay? Or let's take vanadium, okay? Now we know it has argon electron configuration, and then it starts to go up to here to fill up these this row right here. It would have 2 of the 4 S's, and it would have 3 of the 3D filled in. Now remember, valence electrons are in the outermost shell, or the highest floor. We just said these are in floor 4 or shell 4, and these are in shell 3 or floor 3. So who's higher? They're on different floors. They're on different shells. So you can't count these d orbitals when you're talking about vanadium and you're talking about valence electrons. Valence electrons are only the ones in the most outer shell. They can't be on 2 different floors. They can't be on 2 different shells and all be considered valence electrons. Only these 2 would be valence electrons. Just like if you came over to, let's do bromine again, okay? You would have 2 s electrons and you'd have 5 p electrons. So you'd have 7 valence electrons. You wouldn't have no D's. Even if you did have D's, these are in a lower, they're on a different floor. They're on a different shell. Now, remember in the last video I said that the up and like the ones going left to right, horizontal or periods, the columns going up and down that are vertical, those are called groups. And the reason why they put helium over here, even though it should be here, is because they want it grouped in that, right? This last group has its entire shell filled up, okay, right? Because when we did our electron configuration, we would fill in each row at a time, right? So when you get to the end of the row, you go up to the next shell, right? So that means this shell must be filled up if you went to the next shell. So these are very unreactive. Helium, neon, argon, krypton, xenon, very unreactive. They're called noble gases because they're, you know, just like noble metals. They don't react. And they used to call these different groups. This would be like A1, A2, A3, A4, A5, A6, A7, A8, and then these would be B. I think B1, B2, B3, but now they just count them 1, 2, 3, 4, 5, 6. They include it all, and you would go all the way up to 18 because there's 10 and 8 on labeling the groups. I like labeling the groups the way they used to do it, where they separate the D's from the S's and the P's because they're on different floors. They're on different shells usually. So basically, that's the whole gist of what a valence electron is. It's the electrons on the most outer floor, the most outer shell, highest. They're furthest away from the nucleus. That way they can be plucked off and they can go through reactions and stuff. If they're too close to the nucleus, they're not going to, you know, another atom or something that comes along and they want to react, it's not going to grab an electron that's way inside, almost, you know, touching the nucleus. It's going to get one that's, you know, dangling away. The furthest one away it's going to want to get. You know what I mean? And that's all it is. Always remember, science is great.